Okay, so question 3 from covalent bonding section. This one's looking specifically at the molecule of methane and two different diagrams, how we can represent those, both the dot cross diagram and then the stick diagram, as we looked at in the previous question. And it's asking us in the first way is, how do we know that what we're looking at from the molecular formula or from the diagrams that we're looking at a covalent molecule? So there's a couple of ways we can look at that. First is just an identification of the elements concerned, one of which is hydrogen, the other one of which obviously is carbon, and we've got two nonmetals. So because we've got two nonmetals, we know we must have covalent bonding anyway, because we can't have ionic bonding between something if we don't have a metal. So two nonmetals will give us covalent bonding. And also, get rid of this diagram on there, is we've also got a shared pair of electrons here. So we can see one dot and one cross coming from each of the substances. And so we're seeing a sharing of electrons, which is obviously one of the prior requirements for a covalent bond in the first place. And the sharing of electrons is a covalent bond by definition, really. So sharing of electrons is covalent. So we can quite easily see we've got a covalent molecule in that case. Now, two ways, however, though, that they don't represent the molecule very accurately. And again, this is a common limitation of any diagram, dot cross diagram, ionic diagrams, as we see in previous questions again, is that they don't show the three-dimensional structure. None of these diagrams are ever going to really show us accurate three-dimensional structure as to how these things are arranged in space. So three-dimensional structure in space is not very good. Okay, so it's not very clear what's actually going on there. We're not going to see things like bond angles here. The angle between those two hydrogens in figure 2 is not 90 degrees as it's suggested. And always, we never know the sizes of these things. Okay, hydrogen is small. It is a lot smaller than carbon. However, according to that diagram, we can't see that. So the sizes aren't shown very well either. Okay. So that's always a limitation of any type of diagram. But the covalent bond itself, which is what question 3.3 is asking us to do, is just to briefly describe how a hydrogen is bonded to carbon. So we can see it's a shared pair of electrons. So hydrogen started life with a singular electron of its own. So we'll draw that as a dot. And carbon had 4, so we'll just draw one, or we'll discuss one of them. Obviously, there's 4 hydrogens eventually. And the hydrogen donated 1 electron to carbon. Carbon donated 1 electron to hydrogen. They didn't give those electrons away, but basically they were just brought together to create the shared pair here, okay, as it was in, say, that pair there, to give it the same kind of shape idea. And those electrons then come into a common space between the two atoms here, and via an electrostatic attraction, not ionic bonding, but an electrostatic attraction between the hydrogen nucleus, which is in the middle of its hydrogen atom. The hydrogen nucleus attracts to those pair of electrons. The carbon nucleus attracts to those pair of electrons, and it's via an electrostatic attraction there between the two nuclei and the pair of electrons that holds that bond together. And then obviously that would be repeated via the other pair of electrons that would be there, and there, around the 4 bonds of methane that it would have. It's an electrostatic attraction, as I say again, but it's not an ionic bond.